Okay, boss.
Okay, Eduardo, it's
So,
all yours. We can start.
okay, so I've tried to introduce people. Marta and Jana Gabriakova from Bratislava. Uh, they are here because I asked them. And because their work was crucial to convince myself and Pizarro and many of us of the real possibility of allosteric interactions. Though
Hello.
their work was in cardiac muscle mostly. And I was hoping to see Pizarro, but he couldn't come, and maybe Bob Fitz shows up as well. Um, so, okay, so let me start sharing. Share. And let me see if I can put this here. Doesn't matter. And kill this. And make my arrow visible. Okay, so the whole point of the study is to solve the question of activation of the RYR channels of the muscle couplon, skeletal muscle couplon, that are not linked to the HPR voltage sensor, specifically the channel without contact with the HPRs or CAV 1.1, which we call C, do not have a mechanism of activation. We spent half of last meeting giving evidence that the mechanism is not CICR. Hence, these channels, which we call C with Pizarro, because we thought they were activated by calcium, now we know they are not. So they are misnamed, but we'll still call them C. And we also noted the profound differences in structure and mechanism with the RYR2 of cardiac muscle, which of course are activated by CICR. And then we concluded that the mechanism was allosteric by contact, influence from neighboring V channels. This was based on the evidence that C channels are not at all in contact with voltage sensor. From these images, which we showed with the light last time, of the so-called supercomplex of dihydropyridine receptors and ryanodine receptors, imaged by the Fei Sun team in Beijing. Another point of interest is that the pairing of RYR1s has so-called dyad symmetry. It becomes identical upon a 180-degree rotation. And according to the originator of the allosteric idea, Jean-Pierre Janchet, every protein pair that has dyad symmetry known so far exhibits allosteric. And finally, this simulation by Fei Sun's, again, group shows spontaneous aggregation of tetramers via the contact regions that are identified in the structural studies. But only when the simulation is done with the deposited open atomic structure, which means that if there is allostery, it must favor opening. So we are getting now to the actual model. We represent channel gating as a simple transition or reaction, chemical reaction between two states, closed and open, along a path represented by this curve where the height is the potential energy, represents a potential energy called the Gibbs free energy in our conditions of constant temperature and pressure. This profile represents a closed channel. It means that the free energy, GO, of the open state is higher than that of the closed state, GC, implying that an open channel will go spontaneously, roll downhill, so to speak, to the closed state. The bigger the energy difference, the lower the probability of the open state. As you probably all know, I don't have to tell you, the relationship between the constant K and energy is exponential, as follows. And in this talk, I will say that the energy G is given in units of kBt or kT. So we can omit this denominator, and the equilibrium constant will be simply exponential negative of the energy difference G open minus G close or delta G. So let me put some number to this. Say, what would be delta G if we want the RYR to be close, very tightly close, as it is at the resting membrane potential? In the model, we chose a K of 0.005, which means a P open of about 1 in 2,000. So the delta G would simply be the minus log of 2,000 or 7.6. The allosteric effect is introduced as simply a change in the free energy of these states. In case a neighboring open state, okay, I have to make it again visible. I was saying, in case when an open channel is allosterically coupled, it induces an opening effect in our model. Let's say the curve in red. We can say that the neighbor changes the equilibrium toward opening in two ways. It both increases the energy of the closed state by an amount we call here epsilon sub CO, C because it's a closed channel, or the closed state, or because it's paired with an open neighbor, which increases the energy of the closed state. And it lowers the energy of the open state by an amount epsilon sub OO in this case, which is negative. Both tendencies make the open state more likely. If we go back to the equilibrium constant, it will be increased by the exponential of the difference of those two changes. So K sub O, the K altered by a coupled open channel, is equal to the original K times the exponential of this difference, which is a larger number. It is kind of a drag to keep the sign right, but it is also, you can reason it. For instance, if epsilon 0 is big and negative, the exponent will be big and positive and favoring opening. So that's it for the thermodynamics, so-called, the equilibrium effect of allostery. But now we can go to the kinetic effect, which is essential for these programs, for these models. So note that the closed channel energy went up by epsilon CO, and the open channel went down by epsilon OO. In the iron rate theory, which is what we are using here, the rate is determined by the energy barrier, that the distance in energy between the state and the top of the barrier, called the transition energy here, GT. So for instance, this change in epsilon CO subtracts from the height of the barrier. It increases the on rate by the exponential epsilon sub CO. The other change of the closed energy by epsilon sub OO increases the barrier for the reverse reaction. In all, the change in equilibrium, so this is a negative, right? So this will be bigger. In all, the change in equilibrium constant works out to the same thing, but now we have the kinetics, which are given by these modified rates. So finally, for the kinetics, note that we chose here to make epsilon CO about 4 times smaller than the other change. That's a choice. We chose to distribute the energy change, which is the algebraic sum of the two, as 1/5 for the opening rate and 4/5 for the closing rate. The choice means that there is another parameter in this model, which we call nu, and this is a fraction of the charge that we put on the K plus on the opening rate. So in this case, for instance, nu is about 0.2. One last remark to complete the physics of the interaction is that the allosteric effect is reciprocal. If one channel open nudges the other to open, the reciprocal must be true. So all these effects are allosteric effects are reciprocal and equal.
Can I have ask a question?
Perfectly.
Why are you sure that is more easy for a DHPR to open two than to open only one? I would have thought that it would take more energy.
No, but we still are not talking about the DHPR. For a moment, forget about the DHPR. This is very abstract interaction between two RYR1s. And we are going to get to the DHPR. It's a very good question. It's totally relevant. But this is just the abstraction of the pure interaction between the RYR1. So far, we haven't put any voltage sensor here. Voltage is not the matter. Okay, so
And the
you
only
have
reason to think about the difference in energy is the molecular model from the phase soon group, right? That they only interacted in the open state.
no.
No? Oh.
Well, no. That gives you if this allosteric there are several levels of answer to your very good question. If this allosteric interaction is going to solve the problem of C, the problem of C channels is how to open them. So it has to be a positive interaction. The only thing I said is that the phase soon simulation helps one believe in that, goes in the right direction. But the direction is there already in order for this to go anywhere useful, right? For this model to be good. It has to be an opening model. It has to be a change in the red, maybe not as big as here because this is a gigantic change, but the influence has to be in the direction of making it opening more probable. Okay? Okay, so let's go on to something that is very interesting in its own right, which I call the promiscuous master-slave relationship. And master and slave, I must tell you, are denominations that are politically incorrect now, and they were heavily censored in the review article that we circulated the last time. The JGP only allowed me to keep this master-slave terminology in a quote I did from a Chandler paper where he had used it, so it was historical. But then in our part, we had to change to something like leader and follower, I think we said. But here we're among friends, we're going to keep master slave. So this is a couplon in a computer generated now diagram that can change with simulation. And here comes extraordinary. So every V channel, as shown here, influences 3 C channels because of the way that the couplon is organized. But take this C channel here. It is in touch with 3 V channels. One may say that every master has 3 slaves. But this slave will be influenced by these other 2 masters, which in turn influence 3 other slaves each. The master-slave relationship is promiscuous, so to speak. Now consider the reciprocal influence. Every C channel will influence allosterically 3 V channels. In terms of allostery, there are no real masters and slaves. So these two here will affect this one will affect other V's. And the whole couplon in the end will be an allosteric continuum. So the relationship is promiscuous or interlocked and is reciprocal. This is interesting because it makes for the couplon being an allosteric unit and it makes it highly reactive. We found in the simulations that the activation can, under some circumstances, propagate through and occupy the full couplon. And if this thing doesn't explode, it's because of the presence of inactivation, which we will have to deal here too. Okay, but this way of connection makes for interesting calculations of the allosteric energy. Because as I said, the allosteric energy comes from 3 neighbors always. Consider, for example, this situation where all channels are closed except the one that is numbered n+2 here, which is open. Now consider the allosteric change that this channel 2, experiences upon opening. To calculate it, one must take into account interactions with 3 neighbors, 1 and 3 which are closed and n+2 which is open. The energies will all change when 2 opens. So the calculation is a difference between the 3 energies after opening and the 3 energies before. The net difference is listed here. So for this channel 2, the forward rate, the K plus, will be the native K plus, the intrinsic one, multiplied by the exponential of this term, by the negative exponential. And you still have to multiply by nu. Remember nu, the one that distributes the energies in 2. In this way, one can calculate the effective transition rate for every possible transition of every channel. And there is only one because this channel is closed, so it can only open. This channel is open, it can only close. But you still have to calculate all of them. So the model decides every transition in the couplon, one by one. The programming consists of a succession of decisions based on how big the transition rate is. In math terms, this is a vectorial Markov chain, but that's just the name. But before dealing with the simulation, I have to come back to Montserrat's question. We have to tell you how we deal with voltage, and I have to do it slowly. Remember this idea that we talked about last Friday, this old paper of ours. The activation by voltage is treated as just another allosteric influence, another allosteric energy. Allosteric because it happens away from the port itself. And this one is provided by the voltage sensor. The model does not care that there are 4 sensors. It assumes just one energy allosteric term coming from the voltage sensor.
I have to interrupt you, Eduardo.
Yes.
I have to say that I am very glad to see here another guy from Bratislava.
Oh, Milos.
Milos, yeah. He's still working with us, yeah.
He's still working, yeah.
Yeah.
These are 2 memorable postdocs who came at the same time, a long time ago, Ivan Saradnik and Milos Karhan. So I was saying, with them, we figured this out. We figured that the effect of the voltage sensor was allosteric. And we are using that now. The size of the contribution is obviously proportional to the applied voltage. So the K, the equilibrium constant for opening the V channel, will be just the old K of every channel, V or C, multiplied by an electric factor, exponential of the energy contributed by the electricity, by the voltage sensor. So we have e to the minus epsilon sub v. So the only thing of this epsilon sub v is that it is proportional to the applied voltage, which in these simulations is just voltage clamp. It's a constant voltage to make it simpler. So in formal terms that we are using, we need the K plus and the K minus. The opening rate, the K plus sub V now, because it has incorporated the electric term, will be the old K plus times the exponential of the energy change with its own nu. And same thing for the K minus of V. Now, this is formally good, but how much energy to assign, say, per millivolt? As I said, we assume that energy is energy, whether it comes from voltage or not. So very simply, we already showed that to take a channel from a situation in which it is largely closed with a PO of 1 over 2000 to one in which it is half open with a PO of 0.5, we need 7 or 7.6 kT. That's to make it fully open, we are going to need 14 kT or 15 kT. So we know the channels are largely closed at a resting potential of minus 90 and fully or almost fully activated at plus 10 millivolts. That it means that the transition requires 100 millivolts. So we make 14 kT correspond to 100 millivolts. So 1 kT is 7.14 millivolts. In all, we now have rate constant for both types of channels, for every situation, Montserrat. The V channels have the more complicated rate constants because they have an allosteric energy and the energy coming from membrane voltage. So it gets a little bit more complicated for them, but it's just another factor. Now,
Eduardo,
yeah.
not clear to me. You consider these four DHPR channels as independent?
DHPR, well, we don't care. We think we don't know how they do it. We know, but that would be a different paper, right? But in this case, we're trying to make it simple, and we figure it's just an energy. We don't care if it is how many stages it comes or anything. It's just we think that at every voltage there is an energy delivered to the radiating receptors.
Yeah, but I think that if you have four these DHPR channels in couplon, it would be like steeper from this interaction with four of them. That the shape would be the same, but the steepness would be larger of this voltage dependence.
Oh yeah. No, we can calculate that at the end of the talk. We can calculate that, and I think I know where you're coming from, and I think you're right. The fact that we have 4 voltage sensors is very important to determine the steepness of the dependence. But for us, it's an energy. It comes from the 4 voltage sensor. We don't know how many of them have to move in order to get the channel below to open. But this is part of it. This is an energy analysis that will eventually help to decide that. And maybe today we have time to get there. But in the paper in the manuscript that Guido circulated, that point is treated. So it's a super question again. But for now, let's think simply. So now we can program. Now that we have all the rate constant, that's all we need. We can program to decide what happens with the model couplon at all times. And we do a lottery among all channels to decide the next transition according to the probabilities determined by how big those rate constants are. And this is a simple illustration of how it is done. We make a partition of a segment from 0 to 1, within which we have subsegments proportional to every rate constant. Because our couplon has 60 channels, there will be 60 cases, 60 little segments. And then we do a lottery. We draw with a computer a random number between 0 and 1, uniformly distributed, which will point, like this arrow does, at one of the 60 segments. So that is the channel that will do the next transition. Then we have to recalculate again. After the transition is done, at a timing that I don't have the time to explain, but is determined by all these rate constants, the couplon has changed, the state has changed. So we have to recalculate again every rate constant and then repeat the whole cycle. Which takes us to another crucial aspect of the model. Before I can describe how the model did. The time course of flux and the revoltage clamp pulse is as shown here with the well-known early peak and late steady stages. This decay is an inactivation, the transition to another state that is closed but is also incapable of reopening for a while. And there are many ways to account for this inactivation. The simplest option is to go back to the model that Pizarro and I proposed in 1988, where V channels open in response to the voltage, open first and stay put. And C channels open secondarily. In our initial proposal, we said by CICR, and we are now correcting to saying allosterically, and then inactivate. This is by far the simplest way to describe it, but not the only one. But it's a model with least parameters, and it is what we adopted. Now, this assumption has one weird consequence for which we got a lot of pushback from the referees. And we finally convinced them, among other reasons, and other reasons will come at the end of the talk, because with the assumption we could reproduce every observation collected over 40 years of experiment, and all the other alternatives that we could think of did not come even close. So I will explain now the weird consequence. The flux that we describe after correction for depletion is proportional to the product MPO, number of channels times open probability. At a high voltage, say plus 10, plus 20, presumably every V channel is activated, open. And in any good model, most, if not every C channel would also be activated. So PO, my point is the PO for both is probably about 1. And for the C channels at the peak of which is the contribution at the peak of the flux, the PO should be about 1. And for the V channel, the PO is always about 1 at high voltage. So, but N, PO is 1. N is equal because these couplons are symmetrical. They have the same number of C's and B's. However, the peak is 4 times bigger, about 4 times bigger than the steady. So how come the flux is 4 times bigger for the peak than the steady, but N is the same, PO is about 1? What gives? So I hope you see the problem, and I hope some of you dares to make mistakes or risk an explanation.
May I risk one?
Yes.
I think that as soon as some of these C channels close, then the allosteric interaction changes because they are not open anymore. Because I mean, this allosteric interaction always have to go both ways to have this circle, so it doesn't make or release lose energy. And so this is why the steady state is less than peak, because some of the V channels, some of the V channels close. Because this is corrected for
but the problem is why at the peak, when say all Cs or almost all Cs are open, the current, the contribution, that peak is 4 times bigger than the steady, which
well,
at
the
least,
steady is only at the end. So you don't know how would be the steady if you would have only V channels.
I see your point. So you are assuming, yeah,
Yeah, that some of the V's get less activated, not inactivated, but less activated.
yeah, but that wouldn't cover a fourfold. I can see what you're saying. What you're saying is that because the C channels are close and the relationship is reciprocal, the V channel will be partially closed. That wouldn't bring them down to 1/4. I mean, it would be almost impossible. I see you're too good, Sasha, but the
That's just a guess.
but that, yeah, we tried that and it wouldn't work at all. I understand the point. The point is good, but we did go through it in the simulations and it doesn't work. So it works in part, you're right, but that is not the explanation. Anybody else? Big points for Sasha, but anybody else?
Could it be related, Eduardo, to the ratio of V to C's, 1 to 3? That
No, it's
when
1 to 1.
voltage
The reason
goes,
is one. Oh, the reason is 1 to 1.
yeah, but that's assuming the whole thing goes at once. That the whole unit, the allosteric thinks that the whole thing works as a unit.
Yeah.
Maybe it doesn't work as a unit. Maybe there's subunits within the couplon that are working, and that's why it's following more closely the sub 1 to 3 ratio.
It's 1 to 4.
But
And it can be 1 to 5 in some records.
Yeah, but 1 to 3, because if this what's important is because 1 is the V, 3 is the C, so there's 4 channels that open all at once with that single subunit, all right, of that single component, and so it'd be 4 channels open at the peak, and then the maybe it's just the C's that inactivate and bring it down to the other
Yeah,
level.
but that's not possible because you are thinking of a separate masters with 3 slaves each.
Right.
Which are not. Yeah.
But that's what I'm saying is that
Right.
maybe it's not so coupled as you believe it to be.
It would be very inefficient, I think, because you would have to separate. But I see your point too. It's another interesting idea, but it would be very inefficient. Let's put it that way, and inconsistent with for instance, the last paper by Fei Sun showed big, long, interlocked couplons, which is also something that Clara Francini Armstrong has been showing all her life. So yes, it is possible if you dismiss everything we said so far about how interlocked these things are.
Yeah. I mean,
No. Nobody else. This means that nobody read the manuscript.
Yeah.
Can I say something? But
Yeah.
my idea would only account for twofold. But in our 3D structure of the inactivated state,
Mm.
at 2 millimolar calcium, But remember that we were using a lot of ionic strength, so in reality it would be more equivalent to physiological state. Like they adopted a closed channel and it was a different conformation than the resting channel. So what if the C can transition to that, but the interaction between the V and the DHPR doesn't let the other ones, the V's, go to the inactivated state.
Well, that's the point. That's what you're saying is the mechanism behind our hypothesis. Our hypothesis, and that was demonstrated by Jinson Zhao in our department a long time ago. That the reason that there is no CICR is because you have the voltage sensors on top of the RYRs. The moment you remove them, so is the voltage sensors are doing a lot of things. They are the ones who are impeding CICR, and at the same time they are impeding inactivation. So that's an important point.
Yeah. Also, even like I think CICR, I mean, because in the skeletal muscle, even under optimal activating conditions, the channels are closed because of the magnesium. So I think only the DHPR allows to overcome that inhibition. But in isolated channels, as long as you put magnesium 1 millimolar, they will be closed.
Mm-hmm. Yeah. No. The channels are closed. It's the allosteric in this hypothesis. The allosteric does the allosteric influence does the opening.
Yeah.
Because for sure that the voltage that the ones that are under voltage sensors open, and then what we are saying is that we now have a mechanism to eliminate that inhibition by magnesium or whatever the conditions are that make the channels close. So since nobody wants to say
Eduardo, would be a weird thing like a subconductance of the channels or something
exactly. Well, did you read the right. So our idea is that, and we had to fight for that, and our idea is that the C channels have the full conductance and the V channel don't. And the reason they don't have the full conductance is probably are at a 1/4 subconductance, or maybe less, is because of what we were saying with Montserrat. We have the dihydropyridine receptors on top. The dihydropyridine receptor prevents CICR. They prevent inactivation, but maybe they also enforce a channel that is not fully open, or maybe it's they crowd the outlet, and we have all that structure of the hydropyridine receptors on top, and that's a static hindrance of conductance, so to speak. It's crowding of, doesn't conduct so well. So between conductance and the substate, that could be the reason. But so it's, in other words, it's not crazy. No, there is a possibility, and now we can go to the actual model. We kind of satisfied with the physics. It's not crazy, and we can see how it works, how it performs, in other words. So the complete model is simple. It only has 12 parameters. The whole thing is done with 12 parameters. You can see it in the manuscript, what these parameters are. But the model consists of, in our simulation, it's going to be a 60 channel couplon, which is about close to 1 micron long, which is what we see in the muscle, in the structure. So 30 V channels and 30 C channels. The V channels are controlled by CAVs, by 4 CAVs. They can be open or closed, and that's it. And the C channels, can be open or closed, but they also have access to an inactivated state, and in fact to two inactivated states. The other thing we put here in the model, and it won't be justified until later, is that the inactivation is strictly linked to activation. In other words, only the open channels can inactivate, and the recovery from inactivation is to the closed state. So all these two transitions are irreversible, and that's necessary. And that's important. Then there is another inactivated state that I2, that the only thing it does is deepens the inactivation. So you can have longer lasting, more stable inactivation. And both channels are equally allosterically controlled, as we said before. So now we are ready to see how the model performs. I remind you how we do it with the transitions one at a time, in one channel, and then we go back and recalculate and decide the next transition and so on. So here is one run, just a run. In other words, transition until you complete the time of 120 milliseconds. 10 millisecond pre-pulse, 100 millisecond test, 10 millisecond post. And this is the result of the single Markov run. So in blue is the flux through the V channel, which is simply the number of open channels at any given point in time. Because the flux is given here in V channel current units. So this is just the number of open channels. And then this is the C channel flux, which is 5 times the number of open C channels, because we assume that the conductance through the C channel is 5 times more than the conductance through the V channel. 5, not 4. We can discuss why. Okay, so you see that it's kind of bursts of a few channels open, and this is at a low voltage, 2 kT, which is about 15 millivolts. So I have to say that this simulation allows us many levels of comparison. Here we are doing simulations of one couplon. So the simulations of one couplon can be compared with the measurements of one couplon, which would be the measurement that Lothar and Catherine and us and Carlo are doing all the time, which are with calcium monitors at the local level with sub-micron resolution, with all the deconvolving and the correct optical correction to get as good as we can. And so this is at the organellar or couplon level. And these are the observations set by Chernok et al. In our lab a long time ago, one of the hardest experiments we've ever done. He was able to isolate the events at the single couplon level, and the events at the single couplon level at very low voltages are separable, and they are these bursts. They are never a calcium spark. That's a crucial difference. If these were done with cardiac, you would see lots of sparks. You don't see any spark. You see little bursts, separate bursts. And if you increase the voltage, you have more bursts and more even release. Okay, so that's one level of comparison, and it works very well, I would say. Then there are two other levels. This couplon, if you can compare, you can use this simulation to generate the global calcium transient, the global calcium flux or whole cell level calcium flux. And you do it by averaging many of these runs. And because it is one channel at a time, you can also make a small couplon and see what it does, because you get single channel event. We are not going to be able to compare the single channel event, but we can compare in detail to the whole cell feature. I don't think we will have time for the single channel event. They are very interesting, and they are in the manuscript. But let's talk about the whole cell features that we can generate. So here is an experiment of Natalia Shirokova, long time ago, a family of whole cell calcium flux, calcium release flux at different voltages and duration. And here is the simulation. It looks okay, qualitatively, but we have to analyze quantitatively in terms of voltage dependence, kinetics, etc. So first, for the voltage dependence, let's compare the voltage dependence of simulation and experiment. So here is the voltage dependent of the model, peak flux and steady flux as a function of the energy that the voltage provide in kT terms, and we know how to make it correspond to voltage, to actual voltage. So this is the peak, this is the steady, and this is the ratio of the two, ratio peak over steady. So when we fit a Boltzmann to this, a standard Boltzmann, we get a center voltage of minus 37.7 and the kappa or steepness factor of 8.5 millivolt. Now, we compare with the most recent, very careful study of Gustavo Brum's lab with mouse muscle fibers, and they get on average minus 39 millivolt for V bar and 8.9 millivolt for kappa. So the model gets 5 stars for voltage dependence. Now, the ratio, here is the ratio, the voltage dependent of the ratio peak over steady as a function of voltage for the model. And it gets in the middle of the result by a Melzer lab in a very careful study is much higher than what we got with Natalia Shirokova in the lab. And we believe more in Melzer's result because they were very careful in the optimizing the speed of the clamp, which is crucial for determining the peak of the release flux. That's why they got a much bigger release flux. But they got a lot of variation. This is with Fura, this is with Fura FF, or vice versa. But we are satisfied that the model describes well the ratio as a function of voltage. So now we have to go to the kinetics. The kinetics we describe quantitatively in terms of the time to peak and the tau of the decay after the peak. And here we are comparing in black the model as a function of voltage, and for both time to peak and tau. So the time to peak, the tau seems to be quite consistent with a number of papers, measures in a number of papers by the Chernok lab in Debrecen, which are in red. The time to peak systematically become faster or shorter at higher voltages than the very careful measurements of the Melzer lab, paper by Ursu et al. And we think we know why. Is because in our simulation, to make it simple, we make the voltage clamp start instantly. When we put a delay, which makes like a 1 millisecond time constant of rise of those voltage clamp pulses, which makes the calculation much harder, we get these stars, which show that part of the error of our model compared with Meltzer is because we don't take into account that delay, the natural delay in the experiment. So we think kinetics is also well described. So now we're going to an important experiment that the Knox-Chandler lab, Pape et al. Did a very long time ago. What they did was to measure with enormous precision the release flux at very low voltages, like -72, -69 here. So the release flux was so small that they are plotting here the integral of the release flux. In other words, the change in total calcium in the cytosol, because release flux would be the derivative of this and would be terribly noisy. They see very good records of this integral. And here they are plotting the slopes of this curve versus the voltage logarithmically. So this semi-log slope tells you directly and perfectly the valence, the amount of charge in the sensor. Which come to a valence in this measurement, in this very careful measurement of 6.7. In other words, the charge that matters of the voltage sensor is 6.7 elementary charges. So now this is the model. And I don't remember well how many repeats we needed to get these very small openings or integrals to have like that without noise. I think it was 6,400, if I remember well. 6,400 repeats of the Markov run for every curve here. And that takes about a day and a half. This simulation here took about 35 hours of my office computer. So, but we did it like that so we could find the derivative, which is the flux. And here the flux, as expected, is flat and small. So that was well reproduced. And how about the limiting logarithm slope? It's almost perfect match with Chandler's. So the model is getting more respectable as we go. Here is another property. What time is it? Oh, okay. We are close to the end. So here is another property. This is an experiment of classical experiment of recovery from inactivation. You inactivate with a pre-pulse and then you do a test pulse and you see how the peak recovers as you increase the interval between conditioning and test. And the time constant obtained by Sarkozy et al., again, the Debrecen-Chernok lab, was about 100 milliseconds. So here is a performance of the model. In traces are, again, lots of averaging needed. The model recovery in double pulses. And in red, again, repeated the point from Sarkozy. Again, a very good match, I would say, recovery from inactivation. This type of experiment is the one that requires us to incorporate a second inactivated state. Without a second inactivated state, we can't get it. We cannot get this. But now, finally, I get into a more delicate issue, which is what Pizarro and I back in 1997 described as the quantal property of inactivation. So the quantal name was put by Mualem in another similar property that he described with IP3 receptor. But let's put it here, put attention here how it is. This is again a two-pulse experiment. In one case, without the pre-pulse or the conditioning pulse, you get this peak. If you put the conditioning pulse, you now get down to this peak. That is called suppression. And what Pizarro discovered is that the decay during the conditioning release is nearly equal to the suppression of the test. And that extends to all the voltages that you can put here and conditioning. But just to tell you how extraordinary this is, I took just one of these curves of the window, the famous window current that has been done by people to describe inactivation in many channels. This is a T-type voltage-dependent calcium channel, CAV 3.1. But this is the activation curve, and this is the so-called availability curve, which is a complement to one of inactivation. And you see, for instance, that a pulse to this value will activate this much and inactivate this much, suppress this much. Right? So this is extraordinary from the standpoint of conventional inactivation. And this is the complete experiment, again, by the Debrecen crew, where they change the voltage of the conditioning pulse, and they see how this pulse peak is going down, the suppression is increasing. As the decay increases, the suppression increases. And here their plot, decay versus suppression, this is the equality, the identity is given by the line. There is some systematic deviation, but it's almost perfect. So this brings me back to the strange inactivation properties that we assume for the channel. We said the only explanation possible for this that both Pizarro and I and Chernock and all the work that he did came up with was that every channel that opens inactivates. And so you see them inactivating here, and you see them inactivated here. That's why they are equal. That is not how conventional inactivation works. In order to achieve that, the inactivation has to be strictly linked to activation. In other words, only open channels inactivate. And then most channels that are open must also inactivate. So inactivation is obligatory, is fatal, and is linked to activation. And that and the choice of parameters just makes sense. So here is the result. This is now the simulation of that Chernock experiment, full experiment. In black, again, are the model results. This is decay versus suppression, decay in the conditioning versus suppression in the test. So in black is a model. In red are 3 papers, results collected from 3 papers by the Chernock lab. And you can see that even the deviation from identity is similar in the model than in the experiment. So we think that the model did well here again. And this in turn turned out to be crucial for deciding among the many other models that we contemplated and simulated in the manuscript. So this is it. Now I want to wrap up. This is my final what again? Okay, so I'm going to take it slowly. So go back to the virtues of the model and some consequences of its success. And the much bigger discussion again is in the manuscript. So a virtue is that it is simple and consistent with physics, and of course provides the long sought answer to the question of how C channels are activated. We say allosterically. It gets the voltage dependent right unintentionally because we didn't look for it, we just got it. With this very simple reasoning that we did about 14 kT being necessary to saturate the system. The thing just fell from the tree, you know, the exact agreement with measurement. And as we just said, it solves the quantum inactivation mystery, okay? Reproduces the quantum. But what I want to talk a little bit more, think a little bit more, is about the checkerboard array and what we call the skipping pattern and checkerboard array mysteries. Because we ask why the couplon is a two-dimensional crystal. Why why the two-dimensional order, strict order? And why the skipping pattern? So let's take it one at a time. I think and you can interrupt because this is just for discussion. The checkerboard array, which is the orderly array in two rows of the RYR, is done for the purpose of allostery. Because you need the contact in order to have allostery. That's a simple answer. And then, why did it bother with the DICR? Why did it transition from in cardiac CICR to in skeletal DICR, depolarization induced calcium release? In my view, to exert control, strict control, and avoid CICR, which is naturally unruly, hard to control. The couplon of cardiac muscle explodes. This one doesn't. So the voltage sensor does two things, as I said before, and Jinson Zhou demonstrated in the lab, that it is the one that prevents CICR. And now we know, when she said it prevents CICR of the underlying V channel. And now we think it prevents CICR of the C channel also by allostery, because now these C channels are tied to the V channel. They don't escape to CICR, but some Wolfgang Kirsch demonstrated after in Germany, the moment you remove the membrane, the skeletal couplons start to behave like a cardiac couplon, start to have things that are similar to calcium spark. So again, DICR control the channel, but also prevent them from the voltage sensor, the repeating receptor, control the V channel, but also prevent the whole structure from having CICR, which evidently mammalian skeletal muscle doesn't want. But then we get to the issue of the skipping pattern. Why the skipping pattern? Why not have these voltage sensors on top of every channel in the couplon? Okay, so here is again the structure, the super complex image so nicely by Fei Sun or Sun. Imagine that in order to have control by the voltage sensor, nature had to put 4 dihydropyr receptors, bulky pentamers on top of one ryanodine receptor. This obviously conditioned the conductance by this channel, the function of the channel. You cannot have all that and pretend that it's going to be the same as when you have an isolated C channel here. So maybe, and of course it's a hypothesis, it's an interpretation, maybe the skipping pattern is in order to have every other channel free of this hindrance. You control them by allostery, you control them okay, and you don't have on top of them this hindrance. So that's probably the extent of what I would like to say today. There is more in the manuscript, for instance, why there are 4 CAVs per RYR tetramer. If you want to read about it in the manuscript, it's there, but I think I've taken enough time. Okay.
Eduardo, this is super nice hypothesis. Great work. I have a question. Do you think that the Ryan receptors that are kind of slaves could also influence with some mass or dragging force to actually control, to move the voltage sensing domains in the DHPR?
Yes.
In a way that everything's kind of connected, right?
Yes. There cannot be a unidirectional effect. Physics would forbid it. Let me answer this in this way. That's another very interesting point. Which brings me to one of those wrap-up red items that I had about the total charge in the voltage sensor. We said that 14 kT were needed to reliably open the V channels and activate the whole thing at maximum, saturate activation. 14 kBT. Where does that energy come from? It comes from the electric field, right? There is no other source. They come from the voltage sensor. And how much energy can the voltage sensor draw as electrical work from the electric field? Well, you can calculate it. It's 6.7 according to Chandler and according to this measurement now. It's 6.7 electrons moving in 100 millivolts. Right, so it's 0.67 electron volts, and 0.67 electron volts is 30 kT. So half, in answer to your question, half of the energy of the voltage sensor movement is invested in opening the underlying ryanodine receptor, which means that there is less energy now available for whatever else this movement needs to do. So first of all, that is consistent with physics because we have the energy enough. It's enough. It's about half of all the energy available in that movement. But the fact that it takes half of the energy means that it's influencing, as you said, backward to the dihydropyrin receptor. Because now the dihydropyrin receptor, if it is connected, it has 50% less of its energy available. If it is disconnected, now it has 30 kT for the full 100 millivolt excursion. that 6.7 electron elementary charges is also consistent with a number of other molecular data from Fluger and from Olchese, all that. It's all coming together.
Eduardo, and I remember from Clara's data that sometimes you have these incomplete tetrads.
That
So
what?
incomplete tetrads, and you might not have the 4 of them. Maybe you have 2, or you have, you know. So
Right.
so how was the energetics there? You have a minimum,
Right. So
like a minimum
okay.
ratio
From
to be
very
active?
indirect sources, and now consistent with these, we think that the minimum is 3. You need 3 voltage sensors in order to open a channel,
Mhm.
and that's kind of easy to make consistent with this result because as I was saying, in the experiments of Bernard Fluker's lab, he demonstrated that two elementary two charge residues, 2 arginines, have to cross the field in order to produce the transition. Right? So you have 2 charges per dihydropirin receptor. Because the dihydropirin receptor, even though it is a pseudotetramer, only one of those domains participates.
Yep.
So it's 2 times 3 is 6.
Right.
So it's all, as I said, it's all coming
connected.
together.
Yeah.
And also that tells you why you need 4.
To have enough energy, basically.
Because
You have
why you need
Right.
the tetrad is
Exactly.
the first argument in favor of the tetrad.
Yeah.
Yeah, I think the calcium channel, the hydrogen receptor, evolved to have many functions and only devoted one of its pseudo domains to voltage sensing for DC coupling. So now it needs 4 dihydrogen receptor to get to the amount of charge needed for all the work that has to be done.
Well, but also it might be a structural thing, right? Because the right receptors is also a tetrad, so probably you need to distribute the
Oh yeah,
the energy, right?
the interactions and the
Right.
symmetries and all that stuff. Yeah.
Yeah.
No. This is,
yeah.
You know,
That's beautiful.
It's open.
Yeah.
Yeah, I have a comment. So Eduardo, super interesting, and it kind of might close a lot of loops. So that's great. I just was thinking of an explanation about why of the skipping, and considering what you have said, could it be to save calcium in the way that, like, when you contract the muscle, first you have to go from 0 or submicromolar, right? So maybe initially you want to have a lot, and then to maintain it, you don't need so much calcium because it already has diffused. So could it be a mechanism to have a very fast start and then just maintain it with less calcium, maybe, and then make 2 kinds of RYRs? So
But
that
you know all that in skeletal muscle is done with repeated action potential, right? So it's hard to extrapolate from a voltage clamp transient. It's clear that it's done with trains of action, the so-called tetani, trains of action potential.
Yeah.
So but I'm sure there is some of what you said, but it would have to be mixed with that.
I see what you mean. Yeah. Mm-hmm.
Yeah.
But the second set of action potentials, like after it has come down, they are not able to continue unless the muscle has relaxed, right? You know what I mean?
No, every action potential contributes some more until you get to a
Oh, because
tetanizing level. Yeah.
in
It's
the
a, it's
graph,
a it's a it's a balance of release
mm,
and remove. Of course the initial peak of release in the second action potential of a train is a little bit smaller because of inactivation. Inactivation accumulates, but it reaches a steady state. It doesn't; those peaks don't even disappear. And by the way, one of the things we are doing now is applying this same set of simulation. Now that we like them and we think they mean something, we are applying them to trains of action potentials instead of voltage clamp.
Cool.
It's a more difficult computing business, but it's just computing.
Yeah, Eduardo, I was just making me think, there's lots of, structural information from fish, from flies, phylogenetic information about structural array sizes from Clara and all this stuff. Lots of lots of calcium measurements in other species. I was just wondering how all that, maybe you could use all of that information also to inform your model here. All right. I mean, how has this evolved across, phylogenetically, right? You can, the array changes. Does the calcium release control change in a way that's predicted by your, model? I don't know.
Phylogenet.
Yeah. Just look at other
That
species.
looks like more like the Corsi field.
Well, just a thought. I was just thinking the arrays and might not be as organized in a fish as they are in a mammal, and maybe it might tell you something about what's going on in the mammal. That's
Talk to Montserrat also. She made a fantastic
yeah,
finding.
exactly. There's lots of stuff out there to look at.
About
Anyway,
how
just a thought. I think that's another avenue that could be approached. It might not be as NIH provocative, but might be interesting.
So I wanted to tell you, remind you of another anecdote or advance actually. A long time ago, we were in front of a poster in Biophysical Society of Natalia showing the difference between frogs, which have type 3 ryanodine receptors and CICR, frog skeletal muscle, I mean, and rat skeletal muscle, mammalian, which doesn't have CICR. And everybody was scratching their heads, why? And Beth Stevenson, an old colleague, came and said, just for free like that, she said, mammals have 2 triads per sarcomere. And the triads are right there where calcium is needed in the area of interaction of thick and thin filament, whereas frogs and amphibians and fish have only 1 triad per sarcomere, and it's in the Z line, relatively far. You know how important distance is in diffusion. Right? So it's clear to me, she said, the teleological aspect of this, because if you have all that distance, you need a big peak, you need CICR, you need to throw calcium any way you can. But going to the job of doing 2 triads per sarcomere, you can now position them at the interdigitation region. And that solves your problem. You don't need such big a peak. You don't need, and we showed how the peak with CICR was much bigger in frog than in mammal. So that was another philosophical thing.
Yeah, it's interesting stuff. Nice talk, Eduardo.
Okay, thank you. All
Yeah,
right,
it's
guys.
a very nice talk. I remember from this paper from Clara Francini Armstrong that there is like some divide when you go down the evolution tree, that in fish there are still couplons, but below that already couplons don't form. And then you have like calcium release like in crayfish and so on. also in skeletal muscle.
Yeah.
And I was wondering that what makes this difference, but at the time when I was thinking about it, it was not enough sequences made from these lower animals. So it would be thought.
Yeah, CICR and crayfish brings me back to Galveston, Sasha.
Yeah.
Yes.
And Shandor, right?
Yeah. I still wanted to ask you one thing, that how do you imagine that these voltage sensors which interact with ryanodine receptors, these DHPRs, how they are able to prevent the calcium-dependent inactivation of the RYR when, as we were talking last week, that this calcium-dependent inactivation is probably occurring on these EF hands, which are like quite away from these tetrads.
Is this a question for Mike?
Whatever. No, it was a question for you.
Oh,
But anybody can answer.
no, I thought Mike could.
I don't know.
No, my question is kind of a standard for everything, which is that as I tried to show last Friday, this huge molecule is full of allosterics, full of tricks. So if you imagine that this dihydropyrin receptor acting here can open this port here, it can do other condition the protein in other ways, so that they have this calcium site, the hot site here, where the ITP and calcium and caffeine bind, but now they have the master here telling, okay, it doesn't matter. I don't care. You cannot open the channel because it's all interconnected. So your guess is as good as mine how it happened, but it obviously happened. Yep, that's all I can tell.
So, Eduardo, quick question before we go.
No,
So I don't know if I got it correctly.
I'm not in a hurry.
Okay.
I'm not in a
So
hurry.
it's so the seed channels that you have there that are not connected. So the kinetics of inactivation of those channels in your model, could be similar to the kinetics of inactivation of the cardiac channel, for instance, or activation?
I couldn't answer, but it's a good question.
I mean, it's a different isoform, right? But
yeah. No, but I haven't compared actually. I don't have numbers in my head. Okay.
Great talk, Eduardo.
Okay, thank you. All right, guys. Bye-bye.
Bye.
Very
Thank
nice.
you,
Thank
everyone.
you.
Thanks for it.
Bye-bye. Have a
Bye.
nice weekend.
Thank you.
You have still Friday before you. My Friday is already almost over.
Yeah.
Okay. Yeah.
Bye.
Okay,
Bye.
so have
Bye,
a nice
everyone.
day. Bye
Bye.
bye.